On the 8th of July 2026, the CEO of Lumentum stood at a conference in Paris. He said something that stopped the room. The shortage of indium phosphide, he said, could become more severe than the shortage of DRAM or NAND, more severe than memory. A niche laser substrate had become the most strategic bottleneck in artificial intelligence infrastructure, and then came the twist that nobody in that room had fully processed. The country controlling 69% of global refined indium had added indium phosphide to its own export control list. That happened 6 months earlier. China controls the raw material, and China restricted the flow. And the artificial intelligence build-out of the entire Western world was suddenly waiting for permits from Beijing. But here is the part that makes this story genuinely strange. Indium phosphide is not the material China needs to build its own silicon photonics future. China needs it. The West needs it. Everyone needs it. And nobody has enough. This is not a story about China winning a materials war. A material so critical that the country controlling its supply got trapped by its own export controls. So what exactly is indium phosphide? Why it matters more than any transistor? And why the most important supply chain in artificial intelligence is controlled by a byproduct of zinc mining? This is the part nobody explains clearly. Silicon photonics moves data using light instead of electrons. That much most people understand. What almost nobody explains is where the light comes from. Silicon is a terrible light source. It has what physicists call an indirect band gap. When electrons drop energy states in silicon, most of that energy becomes heat rather than photons. Silicon cannot efficiently emit laser light. This is not a manufacturing problem, it is a physics problem. You cannot engineer silicon into a good laser emitter, no matter how advanced your lithography. So every silicon photonics chip that uses light to move data at terabit speeds needs an external laser source. And that laser source is made from indium phosphide. Indium phosphide has a direct band gap. When electrons drop energy levels in indium phosphide, the energy comes out as light. Efficient, controllable, precisely wavelength tunable light. The kind of light that carries data at 160 terabits per second through a silicon waveguide. This creates a dependency that the entire silicon photonics industry has been quietly managing for a decade. You can manufacture the waveguide platform on 28 nanometer equipment that China already has. But you cannot manufacture the laser on anything except indium phosphide. And indium phosphide starts as indium, which is a byproduct of zinc smelting, which cannot scale independently of zinc demand, which China produces at 69% of global refined output. The laser powering the future of artificial intelligence interconnects runs on a constrained material. Geologically limited, byproduct dependent, 69% Chinese. Hold that thought. Because in February 2025, Beijing did something unexpected with that leverage. On the 4th of February 2025, China added indium phosphide substrates to its export control list. Every shipment leaving China to foreign customers now required an individual government permit. AXT, the American company that mines and processes indium in China through its subsidiary Tongmei, applied for permits immediately. In the first half of 2025, no permits arrived. 0. For 6 months, AXT's Chinese facility had product and no permission to ship it. The downstream customers started running down inventory. Epitaxial wafer manufacturers, laser foundries, transceiver makers, data center optical module suppliers. Then, in the third quarter, permits began arriving. Slowly. Unpredictably. AXT's management told investors they could not predict the review timeline for future applications. The export control was not a ban, it was a tap. And then the question that nobody in the room had a clean answer to: what replaces it, and when? Open slightly, closed without warning, reopened on a schedule that only one party knew. Now here is what makes this genuinely alarming. The same material China just put under export control is the material China needs for its own silicon photonics future. China wants to build domestic optical interconnect infrastructure that bypasses Western chip sanctions. That infrastructure requires indium phosphide lasers. The InP substrate supply China just restricted is the supply China's own domestic photonics industry needs. So why restrict it? The answer involves zinc smelting economics and geopolitical timing, a logic that makes more sense once you know where indium comes from. That is what we are going to cover next. But first, the scale of what is at stake. Nvidia committed $2 billion to Coherent Corporation in March 2026. Not $2 billion over 10 years. $2 billion to expand one company's indium phosphide fabrication capacity in Sherman, Texas. That number tells you everything about how serious the shortage has become. Coherent is one of the handful of companies that can grow indium phosphide crystals, slice substrates, and deposit epitaxial layers. It is not a simple process. Growing a single indium phosphide crystal boule takes weeks in precisely controlled furnaces at temperatures above 1,000 degrees Celsius. A microscopic contamination event ruins the entire boule. Yields are lower than silicon wafer production by a significant margin, and the companies with the process knowledge to do this reliably can be counted on two hands globally. Coherent in the United States, IQE in the United Kingdom, Sumitomo Electric in Japan, AXT in China, JX Advanced Metals in Japan, announcing a major capacity expansion in 2026. That is essentially the entire global supply chain for the laser material powering artificial intelligence optical interconnects. None of them can scale instantly. Crystal growth capacity is built in months to years, not weeks. And here is the constraint that $2 billion cannot fully solve. Indium is not mined directly. It is recovered as a byproduct from zinc ore processing. The global indium supply is capped by zinc mining economics. When zinc demand rises, more indium becomes available as a byproduct. When zinc demand is flat, indium supply is flat. No amount of investment in InP substrate capacity changes how much indium the zinc smelters produce. Capital can buy more furnaces. It cannot buy more zinc mines. This is the ceiling that neither Washington nor Beijing has fully incorporated into its strategy. Washington is investing in fabrication capacity. Beijing is controlling substrate flow. Both are managing symptoms of a geological constraint that neither side controls. The indium comes from zinc smelting. Zinc smelting follows zinc demand. Zinc demand follows construction and galvanization markets, none of which are driven by the AI build-out. The irony is almost too precise. The most critical material in the future of artificial intelligence is a byproduct of the steel industry. This geological trap is what makes it different from every other semiconductor shortage. The shortage of DRAM or NAND that the Lumentum CEO referenced was a capacity shortage. Fabs existed. Demand spiked faster than capacity could expand. But the fabs could be built. The indium shortage has a different structure. Indium production is not capacity constrained. It is byproduct constrained. Every ton of indium that enters the supply chain emerges from a zinc smelter. Not because anyone decided to produce indium, because zinc ore contains trace indium that is economically worth recovering during the smelting process. Global refined indium production in 2025 was approximately 1,100 tons. China produced 760 of those tons. That number does not move quickly. Building a new zinc smelter takes years and requires zinc demand to justify the capital. You cannot build a dedicated indium mine. The geology does not cooperate. This is the ceiling that Nvidia's $2 billion runs into. Coherent can expand its indium phosphide crystal growth capacity. Coherent can process more substrates per year with more furnaces. But Coherent cannot increase the amount of indium that enters the global supply. That number is set by zinc economics. And 69% of it flows through Chinese smelters that are now subject to export licensing requirements. So the question becomes, why did China impose those controls on a material it also needs? And the answer is more complicated than strategic leverage, though that is part of it. The deeper answer involves China's own silicon photonics timeline, running about 3 years behind where Beijing needs it to be. China's own silicon photonics program looks different from the inside. CAN-SEMI completed a 12-inch silicon photonics production line in 2025. The Institute of Microelectronics at the Chinese Academy of Sciences has active co-packaged optics research programs. The waveguide manufacturing capability is real. The 28-nanometer deep ultraviolet equipment is domestic. The lithography is solved. But the laser source is not. Chinese domestic indium phosphide substrate production exists. AXT's Tongmei subsidiary in China is a significant producer. But the epitaxial deposition capability that converts a raw NP substrate into a laser-grade material is concentrated outside China. IQE in Cardiff, WIN Semiconductors in Taiwan, Visual Photonics, Epitaxy in Taiwan. The epi vendors that turn Chinese indium into Western laser components are predominantly Taiwanese and British. This creates a structural irony. China controls the indium. Taiwan and the United Kingdom control the epitaxy. The United States controls the laser assembly and packaging through Coherent and Lumentum. And Japan controls a significant share of substrate production through Sumitomo and JX Advanced Metals. No single country controls the complete indium phosphide laser supply chain. The export control China imposed in February 2025 was not aimed at the laser. It was aimed at the substrate, the step in the process that China dominates. Restricting substrate exports gives Beijing a lever over every downstream step it does not control. Without the substrate, the EP vendors cannot produce. Without EP, the laser foundries cannot fabricate. Without lasers, the silicon photonics transceivers cannot function. And here is what makes this lever unusual. China is restricting a material that it also needs. Beijing's domestic silicon photonics programs require the same NP substrates it is restricting for export. So why impose the control? The answer reveals something about how Beijing thinks about timeline. China's domestic photonics infrastructure is not ready to use NP at volume yet. The export control costs China less now than it will in 2028. So impose it now, while the cost is low. Use the leverage before you need the supply yourself. The substrate export control is a tourniquet applied at the point of maximum Chinese leverage. In a supply chain where that leverage is otherwise limited, the Western response moved faster than Beijing anticipated. Nvidia did not wait to see whether the indium phosphide shortage would resolve itself. $2 billion to Coherent in March 2026. Simultaneously, JX Advanced Metals in Japan announced a multi-year NP capacity expansion. IQE signed a multi-year epi-wafer supply agreement with Tower Semiconductor in June 2026. In June 2026, AXT signed a 3-year supply agreement with Coherent for 6-inch NP substrates. The industry responded to the Chinese export controls with a coordinated investment program in non-Chinese indium phosphide supply. Not because the companies wanted to, because Lumentum's CEO warning that the shortage could exceed DRAM scarcity was not an abstract risk assessment. It was a description of what was happening to their order books. The substrate shortage was real in the first half of 2025. The permits arrived slowly and unpredictably in the second half. In May 2026, a fresh batch of Chinese permits brought relief to Taiwanese epi vendors, VPEC and GCS. But the investment in non-Chinese capacity was already committed. $2 billion to Coherent does not get uninvested because a batch of permits arrived in May. It becomes the foundation of a supply chain that does not depend on Chinese licensing timelines. And here is the strategic problem for Beijing. Every month, the substrate controls remain in place. Another contract gets signed that moves NP production capacity outside China's leverage. The window for the export controls to be strategically effective is not unlimited. It is closing with each long-term supply agreement signed in Texas, Cardiff, and Tokyo. The rate of those agreements tells you how seriously the downstream industry has read the February 2025 signal. Nvidia's $2 billion to Coherent is not a hedge. It is a declaration that the AI industry will not wait for Chinese permit timelines to determine its infrastructure roadmap. This is the honest part of this story. The indium phosphide shortage is real. The supply chain is genuinely strained. But the framing that China has a chokehold on AI optical interconnects overstates the permanence of the current situation. AXT's export control situation shows both the leverage and its limits. China restricted the substrate. Permits arrived unpredictably. The downstream industry scrambled. And then the industry invested $2 billion in building capacity that does not require Chinese permits. The geological constraint on indium production is real and structural. But the laser industry has been working on alternatives to indium phosphide for years. Quintessent, a quantum dot laser startup, shipped gallium arsenide-based evaluation kits to AI data center customers. That happened in 2026. Devices generating multiple wavelengths from a single chip. Gallium arsenide sidesteps the indium phosphide supply chain entirely. With the indium bottleneck reaching a breaking point, tech giants are racing toward a radical backup plan, replacing indium entirely. But can physics move as fast as the market? The quantum dot approach is not yet at production scale for data center optics. But the technical pathway exists. Silicon itself is being explored for laser emission through defect engineering and strain techniques, partially addressing the indirect bandgap problem. These alternatives are years from commercialization at the volume and cost that data center optics requires. They are not solutions for 2027. They may be solutions for 2032. But the existence of these pathways means the NP dependency is not permanent. The indium phosphide laser is the critical bottleneck now. It is the material that every silicon photonics system requires in 2026. The timeline for alternatives to reach cost-competitive production determines how long that bottleneck remains decisive. Both sides of this conflict are getting something wrong. Washington's assumption is that restricting advanced lithography prevents China from building competitive AI infrastructure. That assumption is correct for transistor-based compute. It is incomplete for interconnect-based compute, where 28-nanometer equipment is sufficient for the waveguide platform. But Washington has not fully absorbed the indium phosphide dimension. China controls 69% of refined indium production. The February 2025 NP export controls were not countered by any Western restriction on indium ore or processing. The upstream supply constraint is still Chinese. Nvidia's $2 billion investment in Coherent addresses the fabrication capacity. It does not address the indium raw material flow. Beijing's assumption is that controlling the InP substrate gives lasting leverage over Western optical interconnect development. That assumption was more accurate in February 2025 than it is in August 2026. The long-term supply agreements signed in the intervening 18 months have reduced the West's dependence on Chinese permit timing. They have not eliminated the dependence on Chinese indium. The two sides are each partially right and each strategically incomplete. Washington controls the laser foundries and the EP vendors. Beijing controls the raw material and the substrate supply. Neither side controls the complete chain. The AI build-out both sides are racing to lead is sitting in the middle, waiting for substrate permits that may or may not arrive next quarter. A material that should be a footnote is the pivot point of the most consequential technology competition of the decade. Zoom out, and this is the full picture. Indium phosphide is the laser source that every silicon photonics system requires. Silicon cannot emit laser light efficiently. Physics prevents it. Indium phosphide can. Global refined indium production is 1,100 tons per year. China produces 760 of them, not because China planned to control the supply of AI laser material, because indium is a byproduct of zinc smelting, and China runs the world's zinc smelters. That date, the 4th of February 2025, is when the supply chain math changed permanently. Permits required for every shipment. 6 months of no permits in the first half of 2025. Lumentum's CEO warned in July 2026 that the shortage could exceed DRAM scarcity. Nvidia committed $2 billion to Coherent to expand domestic InP fabrication in Sherman, Texas. IQE signed multi-year epi-wafer agreements. JX. Advanced metals expanded in Japan. The West is building supply chains that reduce dependence on Chinese licensing timelines. It is not building supply chains that eliminate dependence on Chinese indium. The geological constraint remains. Gallium arsenide quantum dot lasers are entering evaluation at data centers as an alternative to InP. They are not production ready for 2027. The silicon photonics future. Everyone is building depends on a laser. That laser depends on a material that is a byproduct of zinc mining. Nobody was discussing this 18 months ago. Subscribe if you want to follow where this leads, and leave your answer in the comments. If the InP bottleneck is geological rather than a capacity problem, what does AI infrastructure in 2030 run on? The question that matters for the next 5 years is not whether indium phosphide will eventually be replaced. It will. Gallium arsenide quantum dot lasers exist. Silicon laser research is real. Alternative pathways are being funded at laboratories across the United States, Europe, and Japan. The question is whether they arrive before the InP constraint becomes a hard ceiling on AI infrastructure growth. The Lumentum CEO said in July 2026 that the shortage could exceed DRAM scarcity. DRAM shortages in the early 2000s took several years to resolve through new fab investment. The InP shortage has a geological floor that DRAM did not have. You cannot build a new zinc mine on a short timeline. You cannot grow more indium by wanting more indium. The supply is what the zinc smelters produce as a byproduct, and the zinc smelters produce what global galvanization and construction demand requires, not what Nvidia needs for its optical interconnect roadmap. This is the constraint that $2 billion cannot fully solve. It can buy more substrate furnaces. It cannot buy more zinc smelters. Every AI cluster shipping in 2027 and 2028 depends on indium phosphide lasers. Lasers from indium that comes from zinc mines. The material nobody was watching. The byproduct nobody was counting. The supply chain nobody thought to sanction. Until it was the only thing that mattered. That is where the artificial intelligence build-out of the 21st century is bottlenecked right now. Not at the transistor, not at the lithography machine, at the zinc smelter, at the byproduct of an industry that has nothing to do with artificial intelligence, and everything to do with who controls what AI runs on. In a country that controls 69% of global refined indium production, and is figuring out in real time how much that leverage is worth,